Great. So for our last session of the day, we have Nati Srerbo from TTI Chicago. Also done work on a ton of different machine learning areas, including like fairness and optimization and various other things, especially as it relates to us today, recently thinking about chain of thought and related topics. So take it away.
Okay, thanks. So yeah, so I talk about some stuff we're working on. I should say this is a workshop and this is stuff we're working on. And I'm mostly giving this talk to hear from you. So I really would be happy with comments, interruptions, corrections, questions. I think many in the audience know more about this than I do. And they're all sitting like up front here, so it's good. Let's get started. So I'm going to be talking about what I call iterated learning, and maybe I will actually show my outline. So I'm going to just start by just defining it, giving you some theorems, giving you some basic properties, some like nice, cool open questions, and then about halfway through the talk, I'll talk about motivating this and why I think we should care about this and how it connects with things. But hopefully by the time we get to that, you'll kind of also see it for yourselves. And then we'll reinvent transformers and see how it all ties together. So let's start by just defining the learning model I'm going to be talking about. And that's a learning model of what I call iterated learning. So the basic components there, I have a hypothesis or function, if you want to think about it, that maps from a string of symbols to a new symbol. And the way we're going to use it is we're going to start with our input, and then we're going to iteratively apply the function. It's important it's the same function, so we're going to apply it to the input. It's going to generate a new symbol. We're going to write it here. Then we're going to apply it to all the prefix, which is the input plus our new symbol. We're going to apply the same function. We're going to write the symbol here, and then we're going to iteratively apply our function to prefixes to generate this chain of thought. So this should look pretty familiar. And the important thing here, it's the same function we're going to applying over and over again. Now, when I say same function, right, it operates on prefixes of different lengths, and conceptually, we're going to think of it really that it's kind of a very uniform function. If it's applying of inputs of different length, you can think of like padding the length with an infinite number of zeros, which will also be convenient sometimes when writing these things. But really, we want to think about the same function, right? So for formally, we're going to generate this chain of thought z. So we're going to initialize it to our input, and then we're going to generate each symbol by applying h to the prefix so far. And so we're going to refer to this as the chain of thought iteration of a function h. So for any function h, I can define this hcot t, which takes our input and iterates our function t times, right? So it's defined very formally here. I'm going to use this for appending. So we take our output to get the t plus 1 iterate. We take our output after t iterations and then concatenate applying the function to that, right? Okay, so I said the same thing 7 times. Is there anybody that still has questions about what we're doing here? Good, okay. You are not allowed to say no, yes, okay. So, no, seriously, questions are welcome, even if I blunder and say something doesn't make sense, I can write it. Okay, and the important thing is we're going to look at the, yeah, sorry.
Something in mind here, but formally, I mean, it's just, it's either different functions or you could just output the whole thing at once.
So the important thing is we're going to, okay, so right now I'm just defining how to take a function, which, from sigma star to sigma, and iterate it to get this chain of thought iteration of it. And we're also going to look at the, so I said, I'm just going to define things. So I'm going to start just defining things. So as long as you understand the definition, we're good. And then you can ask questions later about why I'm doing this. And then we're also going to talk about the end-to-end mapping. So this is the mapping from the input all the way to the last character. So this is now throwing away all this stuff in the middle. Okay. And the key here is that if we have some, and maybe this is going to partially answer Umesh's question, we're going to start from some base class of functions, so a simple base class of functions. And this base class then defines in turn this class of chain of thought functions and this class of end-to-end functions. And maybe this is the more interesting ones. It's all the functions you can get just by kind of composing the function with itself t times. But when they say composing with itself, it's not just applying it each time to the output, but applying it to the prefix. Okay, so this is the function, the class of all mappings from input to output they can get with any function in my class. So the important thing here are the function classes. So maybe this answers your question. Misha, the question?
You don't differentiate chain of thought from just predicting. Like when you say chain of thought, it's just like predicting.
I'm going to refer in this talk, what I refer to as chain of thought is just the entire string of symbols. Okay, so the entire you think of as computation. Okay, so I start with the input. I have the entire chain of thought, the entire computation. I'm going to use these words maybe interchangeably, and then I have the actual output, which is the last thing. So I'm going to talk about the end-to-end class, which just maps the input to the end symbol, and the chain of thought, which maps the input to the entire string. Does that make sense? Okay, good. So so now we want to talk about learning these classes. Okay, so we're going to distinguish between end-to-end learning and chain of thought learning. So end-to-end learning is pretty straightforward. I mean, it's basically just pack learning of this end-to-end hypothesis class, right? So, but think of it, that means that we have some, and we're just everything in this talk until the last 5 minutes is going to be realizable. Then, okay? So we just have just some distribution over the input. We have some function from our class. We look at the end-to-end version of it, and we see labeled examples of the input and the final final output. And from that, based on MID samples, we want to learn a function h hat that approximates our output to within error epsilon. I mean, I wrote it here in expectation. It doesn't really matter too much. Yep.
Where's the quantification over capital T?
So a good question. So we are going to, for the most part, think of either. You can think of either capital T fixed, but we're going to really think of how is the complexity behave as a function of T. Okay, so the easiest way to think about it is just think of T. So I define here the class, which is the chain of thought after T steps, or the end-to-end after T steps. You can think about more variants of this. You can easily define something where the computation decides itself when to stop, but I don't want to get into that. It's an unnecessary complication. What I want to understand is complexity is a function of the length of this chain of thought. Okay, yeah.
Just a question. Do you know if Iran's worked with?
Yeah. So this. Okay. Okay. So then we're going to talk about so this is the end-to-end task, and then there's the end-to-end learning, and then there's chain of thought learning. So chain of thought learning, now we're given as training data, not just the input and that last symbol, but the entire computation. So this is similar to Iran's paper, Iran's recent paper. There's a slight difference here that it maybe doesn't make a huge difference for the purpose of the talk, but I believe so the important thing here is that this is not like exactly pack learning, because now we're giving is data, or training data is the entire chain of thought, but what we care about it then predicting is just that last symbol. So that's a bit different than Iran's definition that looked at the task is predicting an entire computation. So here, when I say chain of thought learning, I mean being able to predict that last symbol if I have in training time access to the whole thing. Okay, that everybody good with the definitions? Okay, great. So, my animation is broken, so you're gonna have to close the bottom half of your eyes. Okay, so what can we say here? So how can we bound, like what we want to do is if we bound understand the sample complexity of these learning tasks in terms of the base class H. Okay, so maybe the most basic thing we can say is, how can we bound the hypothesis class H? The most basic complexity measure for the class H is if the class H is finite cardinality. So if the class H is finite cardinality, everything is very easy because the cardinality of the end-to-end class is bounded by the cardinality of H. Okay, there's every function in the end-to-end class is constructed from some class in H, and so and we know that we can bound, since it's just pack learning, we can bound the learning by the log, some complexity of learning by the log cardinality, and we can have a bound in the sample complexity of learning in terms of the log cardinality of our base class H. And this is for the end-to-end task, and in particular also for chain of thought. And we just get more information. I mean, it doesn't hurt us. Okay. This is very simple. This is based on the cardinality of H. But what about if we have some other complexity control over H? So one natural thing to think about is, oh my God, this is completely broken. Okay, so sorry about that. One other thing to think about is what about if we have a bound in the VC dimension of H, right? So this is the real, I mean, we prefer to think of a complexity a bit more generically than just using a low cardinality. So in particular, if H is a binary hypothesis class, so the output is binary, know that if the output is binary, in our setup, the input also has to be binary, right? Because the input is actually output from previous iteration. So the alphabet we're talking now is just binary. And we have a bound in the VC dimension. Can we now also bound the VC dimension of the iterated class? So we can, but not in a particularly satisfying way. Okay, we can only bound it by the VC dimension up to logarithmic factors by the VC dimension of the base class times the generation length. Okay, so times the computation length. So this is kind of, it is a non-trivial upper bound. It does give us a bound on the sample complexity, but it's kind of unsatisfying because the number of parameters, right, is only d. I mean, why should we have to pay sample complexity which is t times d? I mean, it seems kind of very loose. Unfortunately, this looseness is true. So you can actually construct hypothesis classes which have low VC dimension, but the VC dimension and sample complexity of iterated learning does indeed scale linearly with the length of the computation. Okay? So that means that it's now when you want to talk about the complexity of end-to-end learning, we really need to think about not just something like VC dimension. There's something else going on. I mean, we have to what properties of the hypothesis class actually make the end-to-end task learnable with the number of samples that doesn't explode with length. I'll take your question just a second, Srerbo. And just to, maybe I will slightly motivate now, though I hope it's obvious, right? This is what we're doing all the time when we're learning with transformers, right? We have a transformer that has a small number of parameters. We're learning of context lengths of I don't know, what is it now, several million? I don't even remember, the 8 million, is it? Or something like that, right? We don't want our sample complexity to scale with the context length, right? We want it to scale with the number of parameters complexity of our base class. Yeah.
Or something else is more the right notion?
Maybe, but okay, so let me think.
More than VC won't be the right.
Maybe that's a good question. I don't know. So that's so it's very possible. Honestly, I don't know, and it's possible these classes we did not try to specifically construct classes with small Littlestone dimensions. So I don't know the answer actually. Maybe so that'd be very interesting actually if you can bound in terms of Littlestone because it does sit between the low cardinality and the VC dimension. Okay. Yeah.
Just had a small comment that a case where the complexity will put all of it just multiply in a linear map.
Let's get to that. Let me get to that in a second. Okay.
So is the lower bound digit extraction?
Is the
VC lower bound is a digit extraction, or
it's not. I wouldn't say it's digit extraction because this class is not. I mean, we don't define in terms of number of parameters. It's a combinatorial class, so I don't know if to call it digit extraction, but. Let me answer both of those questions in a second. Okay, in the next slide we'll talk about linear functions and then we can answer them. I just want to say that the situation is even worse if you want to move from binary to real numbers, right? So now you can talk if the output is real number, then you can talk about a VC dimension, but you might want to talk, for example, in polarized pseudo dimension or the subgraph dimension, which is kind of the appropriate notion of complexity. And now it becomes completely useless. So we can construct classes which have pseudo dimension 1. But where you iterate them even twice, then they completely explode and have arbitrarily large pseudo dimension and are not learnable. So we need really different complexity measure. Okay, so I don't have Srerbo. I don't have a suggestion for a different complexity measure. Srerbo does, and so I think it's very interesting to see if he's right, maybe. Okay, but what we can at least what we can at least look at is look at specific classes and try to understand. So the most basic class I want to look at is, I think, not exactly the class Matush had in mind, but the linear class, linear thresholds. Okay, so again, so I'd still want to stick to a binary alphabet. So and so now my base class is just the class of linear thresholds. I mean, it's the simplest class I can possibly think of, at least. Okay. So we start with the class of d-dimensional linear thresholds, and I want to clarify. So when I say linear threshold, now I'm just applying a d-dimensional linear threshold to the last d bits in my computation. Okay, and I just iterate that multiple times. Okay. So What's the Vista dimension of the iterative class? Anybody know? What? Okay, so we have one vote for number of parameters. Who agrees with Matush? Usually knows what he's talking about. Right? Who thinks it's less? Okay, it's not going to be less, right? Because who thinks it's more? Okay, so I actually don't know, but at least the best I can bound it. I don't have a lower bound, but the best I can bound it is actually much more than number of parameters. It's d times. So this is what we can avoid the log factors here, but this is kind of what we get before. But we can bound it as d squared, the number of parameters squared at least. So I think that if I took just linear functions, you're right that if I iterate linear function, I get a linear function. But now when I apply thresholds all the time, it's not quite the same. Okay, so maybe you have an argument that.
No, actually, the earlier argument I gave was if you're trying to do the Rademacher complexity, in which case.
No, but that's yeah.
This I was using the DC dimension of linear threshold functions, which is the number of parameters.
Right, but then that gets you the first term here, except you can shave a log factor. But we also have that second term, which is d squared. Okay. Okay, so that already gives us a complexity. This is still at least the complexity independent of t. We can get the sample complexity of end-to-end learning. So the question is now, what happens when we have chain of thought learning? Or does that help us? Okay. So I mean, when we have chain of thought learning, I mean, the obvious learning rule is just now we have, instead of just matching, finding something that matches the whole thing, we have like tons of data points. We can match on each step. Okay. So on the surface, we have m times t examples to learn d parameters, right? So really, you'd expect that we only need something like d over t sequences, because d over t sequences would already give us like d examples for these d parameters. Okay, but the problem is that's not quite true. So there are two problems here. First of all, these are not m times t IID examples, right? They're very dependent. So this maybe goes back to what Srerbo suggested, but it's not exactly online learning because I don't care about the other. And the other problem, which was already also pointed out by Ilan and actually also by authors from University of Washington, I should cite it here in a different context, which is in order to have the end-to-end error be epsilon, then I actually need the error at every step to epsilon over t, because I have at every step I have a probability, it's enough to fail at some point, right? So I need to have a very small probability of failure at every step along the way. Okay. If you combine these things together, you're actually back to the same sample complexity. Okay. So I don't know if there's a statistical saving here. Another thing to compare to is so another thing we can do here is something even more wasteful, which is instead of learning a single. So here we have a single. So just to see why. Okay. So another thing we can compare to is. Instead of learning the same predictor all the time. So I want to emphasize I really have the same function all the time, but I could ignore that and just learn a separate function at each time step. Okay, so this goes back again to what Eran's autoregressive model, because that was the model. Here, even though our model is really the same function, we are still allowed to learn a different function at each step, right? This will be just improper learning. Okay, and if we do that, now we really have m-independent samples for each one of those, okay? And the sample complexity becomes dt times 1 over epsilon. So at least in terms of dt, we don't save, but what we see here is at least there is a saving here because we already see this benefit that because we have fixed parameters, we don't have different parameters at every step, the number of parameters does not scale with the computation length. There's an Eran's model. And we can get length independent, computational length independent sample complexity. But what does the chain of thought give us here over the end-to-end? And I think this is maybe the main thing it gives us. Okay, so the end-to-end learning here, I mean, if we just have the beginning and the end, I mean, if we do ERM, right, the sample complexity is governed by the Vista dimension, which is bounded by d squared. But the problem is that doing this end-to-end task is computationally hard, right? It's not just linear learning because I have to kind of figure out what's going to be in the middle. Okay. In particular, you can show that this is very hard. So this is not, we can prove, we'll prove in the next slide, in fact, that you cannot do this in polynomial time, even improperly. So this is hard to do in time that's polynomial importantly in times polynomial, both in the input in the number of parameters and in the runtime, which is ideally what we would want. Okay, The chain of thought, on the other hand, is really easy. Because of the chain of thought, each one of these just gives us a linear constraint, right? We have every step gives us, it's just a linear, it's realizable linear prediction, it's a linear constraint. All we have to do is solve an LP, actually, an LP feasibility problem. Okay, so this is, I think, the main really benefit here, and representative of what's going on in general. In general, what we'd expect, the chain of thought might also help us statistically. It would be nice to understand when it does. Okay, I actually don't have every very good example where it does, but I would be like to have one. But really, where it helps us, even as a super simple example, is that it helps us at least computationally. Okay, I should say that already here, this is very simple. I'm kind of embarrassed. There's huge gaps here that we don't know. This is an upper bound. I don't know if it's tight. For all I know, maybe it is actually just OD. I think it's not, but I don't know how to show a lower bound here. Okay, and then also for the chain of thought learning, I mean, the fact that even if we have a lower bound of this dimension, that does not give us a lower bound of chain of thought learning because we have more information here. So this is, I mean, is the sample complexity really the same as here? I mean, is this tight, or do we really not gain anything by having all this information, or does it help us? I actually don't know. Okay, and also, can we get maybe a sharper separation from learning separate ones at each iteration? So these are, I think, cool little problems to think about. I mean, they're at least fun. They seem like fun little, basic learning problems that I think really get to the core to this thing that we're doing all the time, which is exactly this iterated learning. Okay, but I want to,
We thought about when it's not like the answer is probability 1, but there's noise in the output.
Okay, I'll talk about it then. So then that becomes much trickier to even define what we're talking about. So that's an unrealizable case, or stochastic at least. We'll talk about that then, I hope, if we have time. Okay. Okay, what I want to talk about now is a bit about how to get this hardness result, because this also goes to like thinking about the expressive power of these things, which is really where I want to get to. Yes?
Where does the D square come from?
What's the D square come to? The D square comes from the fact that if I'm looking at linear predictors over the hypercube, then I only need D bits of precision. Okay, and so actually the number of bits I need to specify the predictor is only D squared, and so it's essentially cardinality bound.
Just like the number of linear thresholds.
Yeah, it's 2 to the D squared, basically, yeah. It's, okay. Okay, so how do we get the hardness result? So we get the hardness result by showing that we can simulate circuits using this class. So any circuit can be simulated by this class. So in order to do that, we'll go through this variant where we have a different predictor at each iteration, a different linear predictor, a different function at each iteration. So remember that in our case, there is the same function applied over and over again, the same function. Let's define a different setup where now for each position t, we have a different function h of t, right? So a function we apply h of 1 here, applied h of 2 here, h of t here. So now our iterated hypothesis is given by an entire sequence of hypotheses. It's a much, much more complicated class. And we can again define the chain of thought class and corresponding end-to-end class. And this is very similar to a run setup, identical to a run setup. And what Eran showed is not too difficult to see is if we have a different linear threshold each iteration, then we can implement a circuit, because we'll just serialize the circuit. Every step will calculate the output of one gate, whether it's a logical gate or a linear threshold, it doesn't really matter. Each one of those we can implement using a linear threshold function that corresponds to that gate and operates in the corresponding operands. And so we can, for every circuit of size s, there's a linear predictor of size s plus n, and that operates for, operates for s steps of computation, where each point in chain of thought exactly corresponds to the output of one of the gates, and the final output is the output of this circuit. Okay, and so what we know that we cannot learn circuits, and so if we cannot learn circuits, we also cannot learn this class. But this class is a class where we have a different linear threshold at each iteration. So what we can show, though, is that you can simulate the class with different linear threshold at each iteration with a fixed linear threshold. Okay, so in particular, for any anything in this class, so for any sequence of linear thresholds, one for each step, you can construct a single linear threshold in much higher dimensionality, but still polynomial in everything, like polynomial in the dimension of all these guys and the number of steps you're going to use them, such that if you apply this linear threshold, this single linear operator to the input, and you do have to run it for more time. So instead of, you have to run it for quadratically longer time, right? So you also have to pad the input with some quadratically large kind of input padding, which kind of we're going to use essentially some sort of positional embedding. So it's just one and a whole bunch of zeros, or a whole bunch of, I guess it should be negative ones, zeros, negative ones. Okay, sorry, this should be negative one. I guess it doesn't matter, but whatever your alphabet is. Then what you get is the final output would be the same. I mean, in fact, you can recover all the outputs of this non-homogeneous, non-uniform computation in different bits of your output. Okay, so that means that you have to work quadratically harder, but if you work quadratically harder, you can still simulate circuits. So that's good enough for the hardness result, because again, I mean, it's hard to learn polynomially sized circuits. If I could learn polynomial time, then I could still learn polynomial sized circuits, just maybe a bigger polynomial. Okay, so this is good for the hardness result. Is it useful as okay, so I said that this is, first of all, I proved the hardness, but now I said this is also going to be a segue to talk about the expressive power. Is this useful as an expressive power result, to say, look, I can simulate circuits. So yeah, I can simulate circuits, but extremely inefficiently and in a kind of stupid way, right? If you really want to simulate a circuit, you don't gain anything here by having a single predictor. In fact, this single predictor is bigger than the union of all these predictors, right? I mean, I'm being extremely inefficient here. This is not a good way to go about doing this. But the thing is, I would claim that I don't want to simulate circuits. There's no point in simulating circuits here. If I wanted to simulate circuits, I wouldn't bother with all this machinery, because circuits are non-uniform, and the whole point here is to be uniform, right? So circuits don't have this like iterative structure. When I want to simulate, it's something that has iterative structure. Okay, so now let's take a break, and I get to tell you about all my fantasies. Okay, so this is really, I mean, let's really step back and think about what is it that we want to learn, and why is this class really, really useful. And let me just tell you what I'm going to do in the next like 10 minutes. First of all, I'll tell you all my fantasies, like what I really want to learn. And then we'll take that and say how I would have invented transformers. Not how, but why I would have invented transformers. Why transformers are really just the exact natural thing for satisfying my fantasies. Okay, so let's see. So what is it I want to learn? Okay, ideally what I want to learn, okay, is anything that I can describe. Okay, and that's possible to learn. You should take a class of all functions that have a small description. And it doesn't matter what your description language you use, some logical descriptions or whatever, you can learn them, right? Because the number of things that have description of length s is just 2 to the s. The local cardinality is just s. You can learn it with some complexity s. Okay, but that's a good specific kind of descriptions. I mean, probably the most useful descriptions are programs. Okay, so you can look at the class of all functions that can be described by a program of length s. Okay, and this can again be learned in some complexity s. Okay, so that's great, and I'd really want to learn that. Okay, and you can learn that, right? So this is just a computational problem. This is learnable with sample complexity s, right? And this is really, I think, the whole goal of learning is learning this. But this is also a bit maybe not. This has issues. So both it's completely non-tractable computation. You say non-tractable. It's not just non-tractable. It's just not computable. Okay, but beyond being non-computable, it's also kind of useless. Because what good will it be if you give me some program that then ran for an extremely long time? I wouldn't be able to use it, right? At test time, I want to learn something to actually use it, and I wouldn't be able to use it, okay? So maybe a better thing to think about is not just learning programs that are short, but also that have small runtime, okay? So we can look at the class of programs that have small runtime, okay? So this is also learnable with time t, because at least the way I look at it, something has runtime t also is description length, the length if you start by reading the program or something like that. And this is, okay, so this is NP hard to learn. NP hard, or ERM is NP hard. So the question is now, is this fact that NP hard, is that good news or bad news? So I am curious, when you hear that something is NP hard, who thinks this is bad news? Okay. Who thinks this is good news? One person, at least there's one optimist here. It's good news, right? Because if NP hard, it means that it's NP, right? I mean, so this is already much, much easier. It's an NP, right? I mean, it's doable. All you need is a non-deterministic Turing machine. I don't know. If you give me a non-deterministic computer, the first thing I'm going to do is learn all seriously, I mean, this would be the complete killer application of a non-deterministic computer. I don't know if maybe you can expect something like this. I don't know. I'm looking at you. Okay, so so this is already much more much more useful. And the thing is that I think this is not only that this is maybe possible with a non-deterministic computer, but this is also maybe sort of maybe possible, not possible, but this is, I think, what, to me, what really motivated learning with neural networks. Because what are neural networks, right? Neural networks is just another way of representing things that are computable in time t, right? Because anything that's computable in time t also has a circuit in size poly t, and which poly now depends on what your exact model of computation here. It's not so important for this for our purpose now. Anything that's dual in time t. You can do with a circuit, and so you can do with a threshold network, and so you can also do with a neural net with any activation function you might want to do. And this is now kind of useful because, okay, we can't exactly. I mean, in fact, it's if we don't have non-deterministic computers, if all you pessimists would think, or okay, you have to be a bit more pessimistic. It's NP hard. It's not enough that P is not equal to NP. But if you think crypto exists at least, then you know that this is not. We can't actually learn neural networks. In the worst case, but still, we're having lots of success with learning neural nets. And this is, to me, still a very good motivation for why neural nets are an excellent model, because neural nets really allow us, like learning neural nets is kind of like learning functions with small runtime. So this is great. Okay. And this is, again, the same as circuits. Okay, so, but when do iterative models come in? So the thing is that in order for things to be tractable, I need the program to have small runtime. But now I'm learning with a sample complexity that also scales with a runtime. This is unnecessary. Like, really, the class I'd really want to learn, and this is now I'm telling you really my fantasy, is to learn the class of programs that have, oops, this L should be an S here, sorry. To learn programs that are both short and have a small runtime. Okay? The thing is that they can be still much run for much longer than their length. Like most programs that you run in polynomial time or run in reasonable time, okay? But still their runtime is much length than the length of the program, right? I mean, unless you never lose loops and function calls and recursions, right? So our runtime is always going to be longer than our program length. In the fact that our sample complexity, if you use neural nets, you're kind of stuck with the sample complexity that scales as a function of your runtime. And that's really a waste. You still would hope your sample complexity would scale with program length, and only your training time might scale with or your compute would scale with the with runtime. Like in particular, as long as your runtime is still polynomial, this is still in P, and if you give me a non-deterministic computer, I'll still be able to learn it with sample complexity. Learning efficiently with sample complexity, it only scales with the program length. So this is really, I think, what we want. And now, I want to like a kind of like reasonable method of doing it. So in particular, in the same way that we do have here, like neural nets are. Why are neural nets good? Why do we learn with neural nets and not with enumerate over fast runtime programs? Because okay, they're hard to learn in the worst case, but they're kind of trainable, right? I mean, we can at least try, right? I mean, we have good methods for dealing with them. In many cases, it works. So what we want is a kind of similar thing here of some kind of class that is trainable in some vague way. Okay, maybe we can make it less vague. Okay, but trainable in some sense, and can actually represent programs with length s and runtime t with a complexity that scales only with s, or maybe s log t. Log t I'm willing to take. And this is going to come up, and that's fine because again t is going to be polynomial, so log t is fine. Okay. Yes. Where did it come from? Where? Why am I here? I'm just being generous. I'm not saying that I know how to do this anyway, right? So I'm saying that even if you gave me something that had some complexity s log t, I'd still be fine because t is still going to be polynomial. Like the thing is that runtime t is going to be polynomial in the input and s and whatever, because otherwise I'm really going to be non-tractable. Like I'm really not going to have a chance here at all, right? And so if t is polynomial in s, then log t is the same as log s. Right, and so I don't mind about log t. Okay, that's kind of why I'm willing to tolerate it. I'm not saying it's necessary, but I'm just being generous here. Okay. Okay. Yeah. No, because no, because of two reasons. Well, let's see. I mean, I didn't even. Let's see what we're gonna get to. But I would say that no. First of all, I mean, I think people. Somebody mentioned it earlier today. Was it? Did you mention it, or they will mention it? Somebody mentioned. I mean, RNNs are. I mean, they have kind of finite memory, right? So maybe they're not so good. Maybe they are also RNNs. My main problem with RNNs is they're not very trainable, honestly. But okay, but let's actually try to get to them. So let's go back. Until now, we talked about these linear thresholds. And can we get here away with linear thresholds? So the thing, I don't care about implementing circuits. That's boring. I don't want to implement circuits. What I want to implement is neural nets, right? What I want to implement is short programs, okay? Do I have a chance of doing that using linear thresholds? And you discuss linear thresholds. And the answer is kind of no, because the problem with this class is it has a very small context length, right? Its context is bounded by a number of parameters, right? And that means that I need d, the number of parameters, at least to scale with the amount of memory my program uses. Okay, and I mean, again, that's too much for me. I don't want to restrict myself to a program that only uses a small amount of memory. I really want the number of parameters to scale just with the program length, not with the amount of memory. You're not convinced. No, you're convinced, but Daniel is not convinced. Okay, he's convinced now. Okay. Remember, though, so we're still talking over binary alphabet, so it's really is memory. I don't even have to talk about log precision, and it's like my life is much simpler. I just need to count. Okay. Okay. So right. So this is not good. So how can we get context length that's much bigger than the complexity, number of parameters? Okay. So there's several ways to do it. I think the easiest way to do it is even just with sparse linear predictors. So this is, I think, already an interesting class. Okay. So this is exactly the same as before, but now I'm looking at k sparse predictor for some k. Okay. The advantage is now I can get very long context length. I can get context length d. Okay. Even though the complexity here is k to the third log d. Okay. So the complexity only has to scale logarithmically with the context length. That's good. Again, logarithmic I'm fine with. Somebody else here. This is, for example, one reason I'm willing to tolerate these log factors. Okay. This is a great, I think sparse linear predictor is a great. Is there an answer to yeah? Okay. So this is a great class. It has low complexity. It's also chain of thought learning is kind of tractable here. So if k is O of 1, this is tractable, right? I'm just going to search over the sparse predictor, but even maybe like 3 sparse predictors is enough for all I know. Okay, like for example, Lanz constructions, for those who are familiar with, are basically just use 3 or can be implemented with 3 sparse predictors. Okay, so maybe 3 sparse, 5 sparse enough. Even if it's not 3 sparse, sparse linear predictors are exactly one of those things that are hard to learn in the worst case, but we learn sparse linear predictors all the time. We have a lot of machinery for that. We kind of understand cases in which it works. We know how to do it, right? So I'd be actually kind of happy with it. I don't know, though, how expressive it is. In particular, I don't know if it can express, short programs. Okay. So can we have some other class? So let's see. What do we want? We want a class that can represent short programs, okay, with complexity that scales only with a program length, or maybe program length log runtime. And preferably also that it's actually tractable to train, at least with chain of thought programming. So can we construct such a class? Do we have such a class? And the answer is yes. It's pretty easy to actually construct such a class. So to construct such a class, we'll basically just directly simulate Turing machines. Okay. So what we'll do is we'll have the following. So I'll describe you now such a class that can implement arbitrary computation, and the complexity only scales as a length of the program, or for a Turing machine, just the number of states of a Turing machine, same thing. N is learnable, the sample complexity that scales with the length of the program, and tractable using COT. Okay, so to do that, we'll use, and now we'll have to go a bit beyond binary alphabet. So for any program length S, and again, program length now, you should start thinking about Turing machine. So this is just number of states of a Turing machine. We'll use our alphabet is going to be triplets of internal state, so which is a set of size S, tape alphabet. Binary tape alphabet is enough. So just binary tape alphabet. If you prefer taking a bigger one, that's no problem at all. As long as it's finite, which is unbounded, it's also enough. And the move the head makes, like right, left, or no move. Okay. In our class is going to be parameterized just by transition tables for Turing machine, right? So transition table Turing machine. Remember how Turing machine work? I mean, we just have for each tape symbol and each internal state. For each table and each internal state, we output like the new internal state, what's tape symbol to write, and where to move. Okay, and what this class would do, remember that our base predictor, this is what I'm telling you is just the base class, right? Not the iterative class. The base class just has to map a sequence of these alphabet symbols to the next one, right? Which is just the next step in the computation of a Turing machine, and that is actually not too difficult to do, right? And you just have to, figure out where the head is, which you can do, what the symbol is, and do it. But let me actually write you exactly how to do it, because we'll want to understand what operations are involved here, right? So let's describe how our base predictor, each one of our base predictors would look like. It gets as input this sequence of symbols indicating the different the computation the Turing machine does. So the first thing it needs to do is to figure out where is the tape head at each at each step of computation. Where was the head? Okay, so at each I needs to calculate that, and how do I calculate that? Just for each position, I just sum up all the moves up to that position. Okay, and now what I have to do, Daniel is already smiling there. The next thing I have to do is for each one, I have to figure out what is the actual, what is the written on the tape at the position that I am. Okay, so I have to look up at the last. For the last time the Turing machine actually wrote into that position, okay? So the largest index I such that the position matches my current position. And then if that exists, then I take that character. If not, then just 0, right? The tape is initialized to zeros, okay? And that's it. Now I have my tape symbol. Now all I have to do is run it through my transition table, okay, to get the output. So that's it, okay. So first of all, we already see that this is fairly simple to describe. And now we can see that this satisfies all our requirements. So first of all, it can simulate any Turing machine with a very simple embedding, right? We just initialize it with the input and then let it run, okay? So it can simulate computation. And the complexity of this, we just have to look at the log cardinality, so just the number of these transition tables, which is just S log S. So we can learn with the sample complexity S log S. And chain of thought learning is tractable. It's super easy. All we have to do is kind of fill up our table, like it's just memorization. So it can be done in polynomial time. Okay, so this satisfies all our requirements. Okay, so we already have a class. But the problem is this class is, again, it's kind of this like short programs, right? I mean, it's not like, but let's see what's going on here. So what are the operations that we're actually doing here? Okay, so this thing is just a lookup table we can implement in a bunch of ways, just some local computation. We can do that with a multi-layer perceptron. That's easy. Okay, so that we already kind of have a method to do. Okay, so what we have to implement are these two operations, which are these global operations we look everywhere. Okay, and if you have paid any attention at any of the talks today, you should already know that these exactly two operations are operations that are very easy to do with attention. Okay, so in particular, this operation. Okay, so in operation, what's going on here? This is exactly what kind of hard attention is doing. It's even easier than an induction head, right? Because I don't even have to look one step forward, right? I just have to look at the, set up the keys to be, the position and some index to see the last index that exactly matches my position, and then read from it. So I can exactly do it, for example, with hard attention. This, okay, the summation I cannot do with hard attention, but I can do with attention that at least spreads out over everything in argmax. So it's not even, I wouldn't even call it soft attention, right? So where I just look at the argmax, but instead of taking a single argmax, I take an average over the argmax. Okay. So if I was designing, so now we progress to the stage of the talk where I tell you how, why I would have invented the transformers if I would have invented transformers, right? Just to clarify, I did not invent transformers, right? Then it's because these are the natural operations to implement this class that solves all my dreams. Okay, and now this is a hard version, and then we don't like hard things because they're not differentiable. We can deal with them, so what we do is just take a soft version of this. Okay, so we can implement that also with the soft version. oops, what's going on here? So a soft version of the same thing. I added here a temperature beta. Of course, you can subsume the temperature beta, inverse temperature beta. You can subsume the inverse temperature beta into the scale of things. I added it explicitly so I can take it to infinity and get over here, get the kind of hard attention that I want. This is with, if you allow me attention with distances rather than inner products, but we know distances and inner products are exactly the same. Anybody that implemented nearest neighbor prediction, those distances and inner products are the same. I mean, we just have to normalize things. Okay, and now we get exactly a representation of this class using our standard attention mechanisms. Yeah, on.
Well, attention can implement this, which is
right.
Or the attention is kind of the natural way to implement.
So what I'm kind of so there's a formal claim, and the formal claim is that attention can implement this. Okay, and again, this is not a new claim, right? So I mean, just to clarify, okay. So this is essentially what's going on. This exact construction is essentially what's going on in a bunch of papers that showed that attention can implement implement Turing machines by Will and is Wei here also. I thought Wei. Okay, but other authors, and this is really simple, right? The reason these papers are not like quite as simple as a single slide is because now we have to get into these issues of like finite precision. How high does the attention have to be? What's the precision of all these things? And this is really the issues that these papers struggle with to make things like actually work. So, and there's also an issue of uniformity versus non-uniformity. So I think the first and the third here really want a uniform model and just have log precision. The Wei and so Colin and Yuning and Tengyu's paper are more don't care about uniformity. I don't care about uniformity either, as long as you're log t. But really make sure everything is like also reasonable norms and is actually learnable. So now there's a bunch of
One comment and one clarification request. So the comment is that I would argue that not only is the citation list going back to like 10 or so, but that's also the derivation. So the derivation of the transformer was from the neural Turing machine, which did start from this. So
you're saying this is not just how I would.
Yeah. The other thing I wanted to just clarify is this is using one of these non-uniform transformers we discussed today, where it has to use a non-uniform positional encoding, because the only way I see it implement is non-uniform positional encoding.
No. So first of all, okay. So now we're getting into it. So let me answer. Actually, I want to quickly answer Ran, and then I'll answer you. So just to answer Ran, so there are two claims here. One is a claim that there's a mathematical claim, which is what's written here, that this is implementable using a transformer, and these guys did a better job at actually saying this in a more in a way that takes account to more things. The other side of the claim is saying this is the natural derivation of transformers. So now, what's natural? This is what I'm telling you. What again, how I would invent it, and what Matush is saying is that this is actually how it was invented. So that's actually actually interesting to talk about later, because at least the paper that popularized transformers did not take this view. But you're right that the origins are predate that paper significantly. So but that again goes to answering that. But this is a software claim. So now going to Matush's claims here. So for positional encoding, the way I wrote it here, I kind of assumed that you have access to your positional encoding. This is a very uniform, but all I need is that there's a super easy positional encoding that each location has I. You just append I. You actually, if you have causal attention, you don't need this. You can easily recover the positional encoding. So you don't need any positional encoding. You can do this with causal attention without positional encoding. You do get, there are some issues here that if you want to do these, use, even if you don't have it in the encoding, so this is, in that sense, this can be done completely uniformly. And in fact, these papers did it uniformly. The issue with doing it, the trade-off here is if you do it uniformly, then you end up with things that scale with, linearly with t. The magnitude, the norm scales with t. The magnitude scales with t. And from a statistical perspective, this might not be desirable. Like, because I'm not sure it might not be desirable, but at least as far as we know, like the guarantees, the length-independent generalization guarantees we have with transformers all have a polynomial dependence on the scale. Okay, so this is work by Ben and Srerbo and by Ambush Tiwari and by this paper, Colin Wei and co-authors. And so that might be problematic. Okay. And so in order to avoid that, you have to have logarithmic log t layers. So now you're non-uniform. So now you kind of have a trade-off. Either you're uniform, but then you lose the statistical currencies, or you're non-uniform, but you only have log t scaling and everything. So that's kind of your trade-off for that. Okay, does that answer the question? But whether you have input to positional encoding is not doesn't matter. In both cases, you're fine with just using causal attention without any positional encoding. I mean, I don't think that's actually how this paper is written, but I'm pretty sure you can do this without any positional encoding and just with causal attention, right? Where's Rion?
Yeah.
Right, you can do this just with causal attention, right? You don't actually need a positional encoding, right? Okay, so great. So we already saw the transformers can implement this, but still transformers, they're not COT, they're not tractably COT learnable, right? Because they have a multi-layer perceptron inside them, even just a multi-layer perceptron. I mean, still they're somewhat easier, but they're not completely learnable. So one kind of fun game to play is, can you design kind of a minimal transformer that will be tractably COT learnable and would still allow representatives? So like a natural candidate is something that looks like this. So it's almost a linear threshold, but it has kind of, it does one of two things. So at each step, it looks at some switch, like the way I wrote it here, just looks at the last 5 bits. If the last 5 bits are all 1, it says, this is an attention step. And now it performs some fixed attention operation, no parameters. And otherwise, it's just linear threshold. Okay, so this is easily, this is learnable. You can, this enjoys the same d-squared sample complexity independent of length, and it's easily tractably learnable because the only steps you have to pay attention when you're learning are these linear threshold steps, which can identify which they are. The attention is fixed. There's nothing to learn there. Okay, the mechanism for the attention is fixed. So this is tractably learnable. I don't know if it can, what its expressive power is. I mean, I think there's a good chance it can capture Turing machines, but I think it's a fun game to play. If like along these lines of, can you design a cellular automata with like 2 states that's Turing complete or something like that. So right, but let's okay. So let's summarize. How much time do I have? Do I have time actually? Oh. Okay. So let's summarize so we can all go and enjoy the marvelous reception that we probably have waiting for us outside. So the type of questions I talked about here are these like very basic, I would call structural questions, or just starting to play with it, really. Okay? But I really think that these, it's important to understand this iterative model. And as far as I know, and please correct me if I'm wrong, because there's a very good chance I'm wrong. I have not seen this kind of setup of iterative learning before, and like understanding the sample complexity of this iterative process when I iterate the same thing over and over again. And again, it's important it's the same thing because I want the sample complexity to not increase with the length, right? If I'm non-homogeneous, if I'm non-uniform, it has to increase with the length. Okay. And this is really what we're doing. It's important to understand it, to understand like how can we learn with very long contexts, and also, it's crucial in order to understand things like length generalization. I didn't talk about it here because here our length was fixed, but in order, if you're not uniform, you can do length generalization, right? So this is essential for that. Okay, I promised I'll talk about non-realizable, but I don't have time for that, which is maybe good because I mean, I don't have much to say. It's really difficult to even, I think it's just defining what's going on here is important, but I think it's really important because what I would like is to move the discussion of autoregressive learning from a generative point of view to a more discriminative reward base, because this is really how we're using it. I mean, when you're using GPT, you care about you're getting the right answer, right? And that's at the end how it's also trained. You don't care that it has good perplexity, okay? But I don't know of any understanding of it in terms of generalization properties, in terms of getting good reward. And I think that this, we need to have some kind of non-realizable agnostic theory of what does it mean for this chain of thought, iterative, homogeneous iterative, or uniform iterative learning to actually generalize well and analyze its sample complexity. So I'll end here. Thank you.
Oh, great. I think to